this video, we are going to learn how to do a hypothesis test for a claim concerning a proportion. So hypothesis testing for proportions. So the first thing, whenever you're going to do a hypothesis test, the first thing you need is a claim concerning a population proportion. Now it is best if this claim is worded as a strict inequality, such as a less than or a greater than, or even a not equals to, but it's better if it's a directional inequality such as less than or greater than. So let's look at an example and start off with the claim. So let's consider the example where we have a random sample of 150 runners who finished the New York City Marathon, and they contain 22 who were over 50 years old. So we're looking at the proportion of runners who were over 50. We want to test the claim that fewer than 20% of the New York City Marathon runners who finish are over 50. So the claim is less than 50% of them, less than 20% of them are over 50. So we're testing a claim of less than 20%. So our claim here is an inequality less than. So our first step here, our claim is that the proportion, which we denote with a lowercase p, is less than 0.2. Claim of less than 20%, or that p is less than 0.2. So first step, state a claim in terms of an inequality, preferably a directional inequality such as a less than or greater than. And in our example, our claim is that the proportion is less than 20% or 0.2. Once we have the claim, we need what is called the null hypothesis, which is denoted with an h sub 0 called h0, some call it ho, could call it h naught, n-a-u-g-h-t, where naught means 0. But the null hypothesis, h naught, is always a statement of equality, always a statement of equality. So for example, in our example then, we have the claim that p is less than 0.2. Our h naught would be a claim of equality, so it would be that p equals the 0.2. Right, so a claim of less than 0.2 leads to a null hypothesis of p equals 0.2. Claim a null hypothesis is always equality, whereas the claim is preferably a directional inequality. Alright, so now that we have our claim and our null hypothesis, we need the alternative hypothesis. And if you followed the directions or the recommendations in this lecture here, our claim was an inequality, and the null hypothesis is always going to be an inequality, so it will end up being the same as the claim. So the alternative hypothesis is denoted as h1. It's an inequality, so for us it will be the same as the claim. Now we say that if the inequality in the alternative hypothesis is a less than, then we have a left-tailed test, because that less than symbol points towards the left tail. If it's a greater than, it would be a right-tailed test, so you can think of the greater than symbol as an arrow pointing to the right tail. And if it is a not equals to, it is a two-tailed test. And I recommend we try to avoid these. We get a lot stronger results if we avoid the two-tailed test and we stick with one-tailed tests, either a left or a right-tailed test. So going back to our example, our alternative hypothesis, h1, is the same as the claim, so it is p is less than 0.2, and it's a less than, which is an arrow pointing to the left, so this is a left-tailed test. Right, and we'll see what that means more later, but basically the area in the left tail denotes unlikely probabilities, and we'll see how we define the left tail in just a moment. Okay, so when we're working with a hypothesis test for proportions, we need to remember that we're working with a normal probability distribution. That's that is based on the assumption in the null hypothesis. Remember, the normal probability distribution is the bell curve. So we have a bell curve where the mean, or the middle of that curve, comes from the null hypothesis, HO. So in our example, we would be working with a normal or bell-shaped curve where the middle is going to be defined to be 0.2. This represents the sampling distribution of proportions, or a distribution of sample proportions. And so we have a distribution of sample proportions where the middle is the true proportion, because that is the value we're trying to estimate. So if our claim of less than 0.2 is correct versus our null hypothesis of 0.2, then instead of being in the middle here would be values close to 0.2, but if we're far in the left tail, then we would be really far away from 0.2, and if the probability of being that far to the left of 0.2 is unlikely, then it's more likely our assumption in the null hypothesis is wrong. So think of the null hypothesis as the assumption under which this test is conducted. By making this assumption in the null hypothesis, that tells us what the middle of our normal bell-shaped curve is, and if it's unlikely to be that value, we will be unusually small, because our claim, or the alternative of less than 0.2 would mean we'd be really far away from the 0.2, so we'd be in that left tail. Now, what's going to determine a small probability? Remember, I said we have the normal curve. If you're around the 0.2, those are likely values. If you're really far away or really to the left in the unlikely region, then that would support a less than 0.2 assertion. So what are we considering a small probability? That is what we call a significance level. So in step 4, we choose a significance level. And you can think of the significance level as a complement of the confidence level that we saw when we did confidence intervals. So for example, a 95% confidence level is equivalent to a 5% significance level. Whereas the confidence level defines likely values, a significance level defines unlikely values, or the probability of being in the tail. So when I was talking about the null hypothesis of 0.2 leaves us in the middle, and the alternative would put us in the tail, then that tail is defined by our significance level. And significance level is usually denoted with an alpha, so we often call it alpha. So in this example, it says use a significance level of alpha equal 0.0225 to test the claim that fewer than 20% of the runners who finish are over 50. So we're going to choose a significance level called alpha. So ALPH is a significance level, and we're going to choose it at 0.025. I choose 0.025 because that will correspond to a one-tailed test when our confidence level is 95%. Because remember, if you're working with a bell curve, the middle 95% is likely, and then the other 5% is divided evenly into the left and the right tails. And so half of 5% would be 0.025, so that would be the probability of being in the left tail, which is the probability of having an unlikely event. And unlikely events mean our null hypothesis is probably wrong, and we would go with the alternative hypothesis. Once we have our significance level, it's time to compute the value of the sample statistic and the standard error. Since we're working with claims about proportions, our sample statistic is the sample proportion, often called p hat, which is x over n. So over here we need our sample proportion, so we're going to call our sample proportion p hat. And remember, sample proportion is x over n. X is a number of successes, that is 22 in this case. Divide that by n, which is 150, our sample size. So we have a p-hat, or sample proportion, of 0.1467, right? So, to recap, we're making a claim that the proportion of runners who are over 50 who finish the marathon is less than 20%. So p is less than 0.2. Our assumption, or the null hypothesis, is that p equals 0.2. So that will be the middle of our normal curve at 0.2. The alternative is the same as the claim, because it's always an inequality, and that's that p is less than 0.2. Less than points to the left tail, so this gives us a left tail test. The probability of being in the left tail is alpha, which is also called the significance level. And we're choosing the 0.025 to correspond to the left side of a 95% confidence interval. So if we work with a 95% confidence level, then we'll take half of the remaining 5% to go into the left tail. So 2.5% in the left tail, so that our significance level alpha would be 0.025, and that is the probability of an unlikely event occurring. And if an unlikely event occurs, it's more likely your assumption is wrong. For this example, we need our sample statistic, which is the sample proportion called p-hat, and that is simply x over n. So when we did 22 divided by 150, we get the 0.14667. Now let's compute the standard error. Remember, the standard error is defined as the square root of p times 1 minus p divided by n. When we did confidence levels, we didn't know p, and so we used p-hat as an estimate for p. Here we're not going to do that because we are making an assumption about p. We are assuming in the null hypothesis that p equals 0.2. So when we compute the standard error, we use the value in the null hypothesis to compute the standard error. So the square root of p, which we assume to be 0.2, times 1 minus p, so 1 minus the 0.2, or 0.8, and divide that by n, which is 150. So the square root of p times 1 minus p divided by n, and we use for our value of p the assumption that is given in the null hypothesis, that p is 0.2. So the square root of 0.2 times 1 minus 0.2 divided by 150. And that gives us 0.0326. So this is our standard error. Okay, so once we've computed our sample statistic and standard error, it's time to compute what we call the probability value, or p-value. And this is the probability of being in the tail. And since we're doing a left-tailed test, it's the probability of being in the left tail, which is the probability that a sample statistic is less than or equal to our computed sample statistic. So this is the probability that any random sample statistic would be less than or equal to what we got in our example. If it were a right-tailed test, the p-value would be the probability of being in the right tail, alright, which is the tails are defined by the sample statistics here. So the probability that our random sample statistic is greater than or equal to our computed sample statistic. That would give us the probability of being in the right tail. If we did a two-tailed test, which corresponded to the not equals, then we would have to take into account not only the area in our specific tail, but the area on the mirror image and the tail on the other side, so we end up getting twice the area of the tail defined by our sample statistic p-hat. So, we are working with a normal distribution. To find the p-value, or the probability of being in the tail, we use a norm dist. Now, since this is a left-tailed test, we want the probability of being in the left tail, where the left tail now is being defined by our sample statistic of 0.1467. So we are looking here then at the probability that any random sample statistic or sample value, we'll just call it x, is less than the 0.1467. So the probability of being in the tail where the tail is defined by our sample proportion p hat. Since this is less than, or in the left tail, we're just doing a regular norm dist. So we'll go to Formulas, Statistical, and find our norm dist. So we want the probability of being in that tail. So we're working with normal distribution. So the norm dist, where x is our p hat, the mean is our assumed middle of this normal distribution. And remember, that assumed middle is the value from the null hypothesis, in this case 0.2. So the value from the null hypothesis is the mean. The standard deviation of a sampling distribution is the standard error. So for our standard deviation, we use the standard error that we computed earlier. And whenever we find probabilities using norm dist, cumulative is true. So once again, we're finding a probability of being in the left tail, where the left tail is defined according to the sample proportion p hat. So when we want to find the area in the left tail, we have to use a norm dist. So x is our p hat. The mean of the normal distribution is the assumed value from the null hypothesis. The standard deviation of the sampling distribution is the standard error we computed. Cumulative is true, and we get this probability here. Let me correct this typo. So the probability that any random sample proportion is less than 0.1467 is 0.05124. Now we need to know if that is a small probability, because small probabilities mean this would be unlikely under the assumption. We are defining small by our significance level alpha. So our significance level alpha defines small, and that's 0.025. So I'll write here to remind you that this defines a small probability. And when we look at 0.05, we see that this 0.05, our p-value, is not less than alpha, but is actually bigger than alpha, so it is not small. You'd have to be less than alpha to be small, because alpha is defining what our cutoff for a small probability. So this then supports the null hypothesis because it's bigger than alpha. If your p-value is bigger than alpha, you do not reject the null. So here we have a rejection rule. Only reject the null hypothesis if your p-value is less than the significance level, because then you would have a small probability, which means an unlikely event occurred under your assumption. Otherwise, you fail to reject the null hypothesis. See, we have an otherwise because our p-value is bigger than alpha, not less than alpha. So we fail to reject the null hypothesis. And you could think of failing to reject is supporting the alternative. So we either reject the null or we do not support the null, right? Reject is, or do not reject. Or you can think of it as reject the null and support the alternative hypothesis, where the alternative hypothesis is the claim. So we will either reject the null and support the claim, or we will not reject the null and not support the claim. It's probably a little easier to just think you're either supporting the null hypothesis or you're supporting the alternative hypothesis. When your p-value is bigger than alpha, you support the null hypothesis. When the p-value is less than alpha, you will support the alternative hypothesis, which is the claim. So if p-value is bigger than alpha, support the null hypothesis. If p-value is less than alpha, support the alternative hypothesis or the claim. So if the p-value is less than the significance level, reject the null and support the alternative. Otherwise, fail to reject the null or support the null. P-value bigger than alpha, support the null. So our final conclusion here is that the sample data do not support the claim. We supported the null hypothesis, not the claim. So the sample data do not support the claim. The sample data do not support the claim that fewer than 20% of the runners who finish are over 50. Okay? Let's do another example. I want to do another example, and this time we'll do a claim of greater than. So we will use the same data here. 150 runners contain 22 who are over 50, but we're going to test the claim that more than 10 of all finishers are over 50. So in our claim here, the claim is that P is now greater than 10%. So here we have a greater than claim. The null hypothesis, HO or H naught, is always a statement of equality, so this is that P equals 0.10. Right, so the claim, statement of inequality. Claim of greater than this time. P is greater than 10%. Null hypothesis, always a statement of equality. P equals 10%, and this is the assumption under which the test will be based. Then we have our alternative claim, H1, which is going to be the same, or our alternative hypothesis, which is going to be the same as the claim. So P is less than 0.1. And then we choose our significance level alpha, and we're going to do a 0.025 again, because now it's a right-tailed test, but still a one-tailed test. So since it's a one-tailed test, we'll use the area in the right tail. If we have a confidence level of 95% in the middle, then the area in the right tail is 0.025. So this defines unlikely values. So it defines unlikely values, or equivalently small probabilities. Unlikely values, small probabilities. And now we're ready to compute our sample proportion, P hat. We did that before. That was the 22 out of 150. So there's our sample proportion of 0.1467. We need our standard error. The standard error is going to be different than the previous example because the standard error is based on P, and this time we're assuming that P is 0.1 rather than 0.2. So we're going to do equals the square root of 0.1 times parenthesis 1 minus 0.1, which is 0.9, divided by n, which is 150. So the square root of 0.1 times 1 minus the 0.1 divided by 150 to give us our standard error, where now P is assumed to be 0.1, and we get an even smaller standard error than we had before. Once we have our P hat and standard error, we're ready to compute the P value. This is now a right-tailed test. This is now a right-tailed test, so we want to find the area in the right tail as defined by P hat. Area in the right tail. And when you're doing an area in the right tail, you need to do a 1 minus norm dist. So we'll go equals 1 minus, then we go to our formulas, statistical norm.dist, and x is our p hat, our sample statistic. The mean is the assumption from the null hypothesis, so that's 0.1. Our standard error is the standard deviation is the same thing as the standard error when we're doing these tests. Cumulative is always true, so we get 0.02838. Notice again that this p-value is bigger than alpha, so yet again we support the null hypothesis. We support the null hypothesis. Alright, so our conclusion is that the sample data do not support the claim, because we supported the null hypothesis, not the alternative, and the alternative is the same as the claim. Oops, I typed this wrong. This is a greater than. Right, a claim a greater than. So the sample data do not support the claim. Okay, let's see. Do not support the claim. Sample data do not support the claim. So we got two do not supports. Now what's interesting here is we did one that the claim was less than 20% did not support. So we thought, okay, how about greater than 10% did not support? Let's take a look at how that corresponds to a confidence interval. Because remember, we are setting up these tests so that the left and right tails have 0.025 in them, which would correspond to a 95% confidence interval. So let's look at the confidence interval here and see why we couldn't support a less than 20% or a greater than 10%. So what we need is our sample statistic p hat, and that is the 22 divided by 150. We need our standard error, and when we do the standard error for the confidence interval, remember that we have to estimate our p in the formula with the p hat. So square root of p, we're going to use our p hat times parentheses 1 minus that p hat divided by n, which is 150. So we'll have a standard error that's actually in between the other two, because 0.1467 is between 0.1 and between 0.2. Now we need our margin of error, and so for a 95% confidence interval, remember that's 1.96 times the standard error, so that's about 2 standard deviations from the mean, 0.0562, and now for our left end point, we're simply going to subtract the margin of error from our p hat, so sample proportion p hat minus margin of error, so our left endpoint. Notice 9%. That is not bigger than 10%. 9% is less than 10%, hence why we could not support a claim of greater than 10%. Let's look at the right endpoint. Remember, we could not support a claim of less than 20, which means we should have a right endpoint bigger than 20. So equals our sample proportion p hat plus the margin of error, and indeed we get something bigger than 20%. Even though it's just barely bigger, it's still bigger than 20%. So we are 95% confident that the population proportion of those runners who finished the New York City Marathon who are over 50 is between 9% and 20.3%. So we see we cannot make a claim of less than 20% because it could be bigger, it could be up to 20.3%. Can't make a claim of greater than 10% because it could be less, it could be as small as 9%. So you're probably wondering, why didn't we just use the confidence interval to establish those claims? And it's because when we use the confidence interval, we're making an assumption about, well, we're using our sample p hat when we do the standard error, rather than actually making an assumption and using that assumption for the standard error. So it's just better practice to do a hypothesis test. There can be times where the hypothesis test and the confidence interval don't jive quite as nicely as they did here. So it's always best practices to do hypothesis tests rather than simply rely on a confidence interval. Now I wanted to do one more example here, but we will save that for another video. So these are claims about proportions when you just have one proportion. So to recap the steps, you always start with a claim concerning the population proportion. It is best to use a directional inequality such as less than or greater than. You need a null hypothesis, H0 or HO, which is a statement of equality, always a statement of equality, and it's the assumption under which the test is conducted. You need an alternative hypothesis, H1, which if you made you stated your claim as an inequality of less than or greater than, it will be the same as the claim. When it's less than, you have a left-tailed test. When it's greater than, you have a right-tailed test. If it's not equals to, you have the two-tailed test, but we try to avoid these. The sampling distribution we're working with is the normal probability distribution, or the bell curve, where the mean is based on the assumption and the null hypothesis. So the middle of the bell curve is based on HO. We choose a significance level, which is the complement or opposite of the confidence level, and that will define our, since the confidence level defines likely values, the significance level defines unlikely values or small probabilities. Then we will compute the value of our sample statistic p hat, which is x over n, and the standard error, where the standard error is the standard deviation of that sampling distribution and is found computing the square root of p from the null hypothesis times 1 minus p divided by n. We will compute the probability value, or p-value, and that's the probability of being in the tail as defined by our p hat, our computed sample statistic. If we're working with a left-tailed test, then our p-value is the probability of being less than that sample statistic. If we're working with the right-tailed test, the p-value is the probability of being greater than our sample statistic. If it's a two-tailed test, let's fix this spelling. If it's a two-tailed test, then the probability is twice the area of whatever tail we got from our p hat. The initial conclusion was when we either rejected or supported the null hypothesis. So our rejection rule, reject the null hypothesis if your significance, if p-value is less than your significance level. Otherwise, you fail to reject, or you can just say support your null hypothesis. And your final conclusion is a sentence. Either the sample data support the claim. So if you reject the null hypothesis, then the sample data supports the claim. If you fail to reject or supported the null hypothesis, the sample data do not support the claim.